this module. You will learn about the classification of elements into S, P, D, and F blocks of the periodic table. We have studied that the position of an element in the periodic table is based on its valence shell electronic configuration. Based on the type of atomic orbitals which receive the last electron or differentiating electron. These elements are categorized as S, P, D, and F block elements. However, there are two exceptions to this classification. The first exception is helium. Based on its electronic configuration, it should be placed in the S block in the periodic table. But it is placed in the P block with the other group 18 elements. This is because, like other group 18 elements, helium has a completely filled valence shell and as a result exhibits characteristic properties of other noble gases. The other exception is hydrogen, which has only one electron in the s orbital, and therefore can be placed in group 1 with other alkali metals. However, hydrogen can also gain an electron to achieve the nearest noble gas configuration of helium, and hence can be placed along with halogens in group 17. Therefore, it is considered as a special case and is placed separately on the top of the periodic table. Let's now learn about the S block elements. The S block of the periodic table consists of elements that have the last electron entering the ns orbital. The alkali metals in group 1 and the alkaline earth metals in group 2 of the long form of the periodic table belong to this category. These are soft metals with low melting and boiling points. With the valence shell electronic configuration of ns1 and ns2 respectively, these elements have extremely low ionization enthalpies. That is, they easily lose their outermost electrons to form unipositive ions in the case of alkali metals, or dipositive ions in the case of alkaline earth metals. Therefore, the compounds formed by the S block elements, with the exception of those formed by lithium and beryllium, are ionic in nature. Due to low ionization enthalpies, S block elements are highly reactive and therefore are never found in pure form in nature. They always occur in combined form in nature. For example, magnesium occurs in the combined state as carbonates, sulfates, chlorides, and silicates, but never as pure magnesium. The metallic character and chemical reactivity of S block elements increases as we go down the group. Now let's discuss the properties of the P block elements. The elements of group 13 to 18, situated at the right side in the long form of periodic table, belong to this block. The P block elements, together with the S block elements, are called the representative elements or main group elements. The P block elements have their last electron entering the p orbital. This results in an outermost electronic configuration varying from ns2, np1 to ns2, np6 in each period. At the end of each period is a noble gas element with a stable configuration of Ns2Np6. The p block consists of metals, nonmetals, and metalloids. The non-metallic character increases across a period and the metallic character increases as we go down the group. The p block elements form compounds by loss or gain of electrons, or by sharing the valence electrons. That is, they form both ionic as well as covalent bonds. Two chemically important groups of p block elements are Group 16, the chalcogens, and Group 17, the halogens. The elements of these two groups have high negative gain enthalpies, and they readily gain 1 or 2 electrons to attain the stable noble gas electronic configuration, which is Ns2Np6. For example, chlorine, belonging to the halogen family, readily accepts 1 electron to attain the nearest inert gas configuration of argon. On the other hand, oxygen belonging to the chalcogen family needs to accept 2 electrons to attain the inert gas configuration of neon. The group 18 elements having the electronic configuration Ns2Np6 are called the noble or inert gases. All of them exist as monoatomic gases. Noble gases exhibit very low chemical reactivity because of their completely filled outermost shell. Next, let's look at the d block elements. The elements belonging to group 3 to 12 in the center of the periodic table are called the d block elements. As the differentiating electron or the last electron enters into the penultimate or second outermost shell, that is, the n-1 d orbital, they are referred as d block elements. These elements have an outermost electronic configuration of n-1 d1 to 10 ns1 to 2. The d block elements are placed between the s and p block elements. They exhibit the transitional or intermediate behavior between the more active metals in S block and less active elements in the P block, and are hence called transition elements. Small size of atom, high nuclear charge and unpaired electrons in d orbitals impart characteristic properties to the transition elements. These properties are: all the transition elements are metals and they exhibit variable oxidation states. Due to their ability to change oxidation states, most of these transition metals and many of their compounds are used as catalysts in many industrial processes. For example, iron is used as a catalyst in the Haber process for the synthesis of ammonia. Similarly, nickel is used as a catalyst for hydrogenation of oils. Most transition metals form colored compounds. For example, MnCl2 is a pink-colored compound, while ferrous sulfate is a green-colored compound. These elements and their ions are usually paramagnetic. That is, they are attracted to external magnetic fields because of the presence of unpaired electrons in their d orbitals. For example, the elements iron and nickel and their ions Fe+3 and Ni+2 exhibit paramagnetism. It is important to note that zinc, cadmium and mercury are not considered as transition elements, as they do not share the usual characteristics of transition metals. This happens because, unlike other transition elements, these elements have completely filled d orbital with electronic configuration of n-1 d10 ns2. At the bottom of the long form of periodic table, there are two rows of elements that belong to the F block. These elements have their last electron entering the F orbitals and exhibit an outer electronic configuration of n-2 F1 to 14 n-1 d0 to 1 ns2. Since F orbitals are present in the antipenultimate shell, or the shell inner to the penultimate shell, these elements are also called inner transition elements. There are two series of F block elements with 14 elements each. The elements in which the differentiating or the last electron enters into the 4 F orbitals are called lanthanoids, whereas the elements in which the last electron enters into 5 F orbitals are called actinoids. They are all metals with high melting and boiling points. Like transition metals, they too form colored salts and exhibit variable oxidation states, the most common oxidation state being 3+. Actinoids can exhibit a much larger number of oxidation states as compared to lanthanoids. Therefore, they have a more complex chemistry. Unlike the lanthanoids, actinoids are radioactive in nature. Very few of them, like thorium, uranium, occur in nature, and most of them are artificially made by nuclear reactions. The elements after uranium are called transuranium elements. Apart from classifying elements into S, P, D, and F blocks, the periodic table also shows the classification of elements into metals, nonmetals, and metalloids. Metals have been listed on the left side of the table and form 78% of the known elements. Metals generally exist as solids at room temperature. An exception is mercury, which is liquid at room temperature. Metals usually have high melting and boiling points. With the exception of gallium and cesium, which have very low melting points of 303 Kelvin and 302 Kelvin respectively. Metals are good conductors of heat and electricity. Metals are malleable, that is, they can be flattened into thin sheets, and are ductile, which means they can be drawn into wires. These properties are in direct contrast to those exhibited by the nonmetals that are placed on the top right side of the periodic table. Nonmetals are usually solids or gases at room temperature with low melting and boiling points. Exceptions are boron and carbon, which have high melting points of 2300 and 3930 degrees Celsius respectively. It is also important to note that bromine is the only nonmetal that exists in liquid state at room temperature. They are poor conductors of heat and electricity. Solid nonmetals are brittle, non-malleable, and non-ductile. Across a period, as we move from left to right, there is a transition from the metallic behavior to the non-metallic behavior. Elements like silicon, germanium, arsenic, antimony, and tellurium in the P block of the periodic table exhibit properties of both metals and non-metals, and therefore are called semi-metals or metalloids. You have now reached the end of this module. In this module, you learned that the elements of a periodic table are categorized as S block, P block, D block and F block elements based on the name of the orbital which receives the last electron. The exceptions are hydrogen and helium. Groups 1, 2 constitute the S block. Groups 3 to 12 constitute the D block, and groups 13 to 18 constitute the P block. Elements in the last two rows at the bottom of the periodic table are called F block elements or inner transition elements. The F block elements of the series in which the electrons are in 4f orbitals are called lanthanoids. The elements of the series in which the electrons are in 5f orbitals are called actinoids. Apart from classifying the elements into S, P, D and F blocks, the periodic table also shows the classification of elements into metals, nonmetals and metalloids. Metals occupy the left side of the periodic table, followed by few metalloids in the P block and finally by the nonmetals. The metallic property of elements increases as we move down a group and decreases as we move left to right across a period in the periodic table.